crystalline solids. So we were talking a lot about the details of how the different atoms are put together. Now we're going to step back and look at the big picture. So crystalline solids have this regular repeating order. We can divide these into categories. We can talk about molecular solids, ionic solids, and atomic solids. And then atomic solids can be divided into non-bonding, metallic, and network covalent. So this is the big picture. Molecular solids have molecules. These terms are not meant to confuse students. A molecular solid is a solid composed of molecules. And so the individual units are molecules, not atoms or ions, and they're held together by intermolecular forces. Examples are ice, which is solid water, or dry ice, which is solid carbon dioxide. What's holding the individual water molecules together? Intermolecular forces. What intermolecular forces water have that's the strongest? Hydrogen bonding. So it's the hydrogen bonding between nearby water molecules that holds it together. Intermolecular forces, though, are weak. And so molecular solids tend to have low to moderately low melting points because it doesn't take a lot of thermal energy to overcome those intermolecular forces. The next group is ionic solids. In an ionic solid, the individual particles are ions. Okay, so things like table salt, sodium chloride, or calcium fluoride, CaF2. These are held together by ionic bonds. The coulombic or electrostatic attraction between positive and negative charges. Ionic bonds are very strong, far stronger than intermolecular forces. Ionic compounds generally have very high melting points. The coordination number represents the number of close cation-anion interactions. So the more interactions you have between cation and anion, opposite charges, the lower the potential energy. So we had looked at all these crystal structures where the individual particles, we were just calling them atoms. When you have ions now, you've got a balancing act. You've got coordination number to consider. You also have charge neutrality. You have to have the right number of each kind. And then you can also have different ion sizes. And so we'll just look a little bit at how that affects crystal structure. If we have cations and anions of similar size, they're likely to arrange themselves in this way. Cesium chloride makes a simple cubic cell where the chloride ions are in the corners and the cesium atom is in the middle. That's a coordination number of 8. And each unit cell has one of each ion. So if you looked at the cesium ions would have their own cubic unit cell. This is not body-centered. This is simple cubic. Simple cubic looking at the chloride ions, and then the cesium fits in there. Calcium sulfide has the same structure. What if we have different sizes? Here's sodium chloride. So the chloride ions are big, the sodium ions are small. Charge neutrality is going to limit the coordination number to 6 because we can't have more of the little ions than we have of the big ones. Yeah, we could fit more in there probably, but then it wouldn't be charge neutral, so that's not going to happen. In rock salt, you have chloride ions in a face-centered cubic structure, and the sodium ions are fitting into the spaces in between them. So if we look at this side, here's the face-center cubic structure with the chlorides, and the sodium ions are just in the spaces in between. Each unit cell is going to have 4 cations and 4 anions. If we have a larger size difference, this is zinc blend. Some of these, zinc sulfide is a compound, but it can crystallize in different forms, and then those different forms have different names. So zinc blend is a particular crystal structure of zinc sulfide. So here we've got the sulfide ions, which are the big ones, in a face-centered cubic structure, and the zinc ions are filling in half of the tetrahedral holes. I'll show you what a tetrahedral hole is in a minute. But again, each has 4 of each ion. So charge neutrality dictates that we've got 4 zinc ions for 4 sulfide ions. If we look at this zinc ion and these sulfur ions that it is directly touching, it's directly touching 4. And 4 things make a tetrahedron, right? So this is in a tetrahedral hole. It's in a hole between 4 sulfide ions. So there's the 4 sulfide ions. They form a tetrahedron, and the zinc ions in the hole. Yes?
So when those are all together, like in one, every single one of those angles then is going to be perfectly 195?
Yeah. So you have this repeating pattern of the sulfide ions in that face-centered cubic structure, and then there are holes, these tetrahedral holes. Only half of them have zinc ions in them. If you have unequal charges, like in calcium fluoride, the calcium ion is a +2 and the fluoride ion is -1. And so here we've got the calcium ion with the face-centered cubic structure. And then the fluoride ions now, we need twice as many of them, so they're filling all the tetrahedral holes. And each of these unit cells will have 4 calcium ions and 8 fluoride ions. And here's some other examples. And so mostly I'm just telling you about this so that you know it exists. You can imagine that things could get pretty complicated, right? Because what if you have polyatomic ions in here instead of just monatomic ions? And what happens when you have a hydrate and you've got water molecules getting in there as well? You can imagine that some of these things become rather complex. So those were the ionic solids. Atomic solids have atoms. What kind of forces do atoms have to attract each other? Dispersion forces. That's all they've got. Because an atom can't have a permanent dipole. So atomic solids are held together by dispersion forces. Non-bonding atomic solids. They're just held together by weak dispersion forces. Are they going to have high or low melting points? Low. Crazy low, actually. The only examples that we know of are noble gases in their solid form. Those are the only ones we know of. They have very low melting points. The melting point does increase with molar mass. And these are going to form closest packed structures to maximize coordination number and minimize distance. Metallic atomic solids. These are metals. The metal atoms are held together by metallic bonds. We talked about the sea of electrons, right? These are also going to form closest packed structures. Here we've got nickel and zinc, and so the zinc atoms are going to be held together by their valence electrons pooling around them. The melting points here are going to vary a lot. We know that mercury is a liquid at room temperature. Gallium has a melting point that's low enough it'll melt in your hand, but then other things like iron melt at very, very high temperatures. And so it varies. And then we have network covalent atomic solids. Here the atoms are held together by covalent bonds. Now you might think, well, isn't that just a molecule? Isn't this a molecular solid? No, this is different. Here with carbon, we have 2 of the forms of carbon, diamond and graphite. In a diamond, each carbon atom is covalently bonded to 4 other carbon atoms. And those covalent bonds continue throughout the whole diamond. So in essence, one diamond is a giant molecule of carbon atoms. A molecular solid has discrete molecules held together by intermolecular forces. Network covalent solids are held together by covalent bonds throughout the whole thing. Yes?
Did you say each diamond is a whole molecule?
Each diamond is essentially one molecule because it's held together by covalent bonds.
That's why they're so hard on you?
And that's why they're so hard, because the covalent bonds are strong and they're in all these different directions. Graphite is also a network covalent solid, but here we have layers. There's a layer of carbon atoms that are bonded to each other covalently, and then there's another layer and another layer, but those layers are held together by dispersion forces. And that's why graphite is soft and slippery, and it makes great pencil lead, because when you press it on paper, it leaves some of itself behind as you move the pencil over the paper. Graphite is used as a lubricant. Yep. Because it slides, it's slippery with itself. Because it's individual layers that are held together by weak intermolecular forces. And so it's very easy to slide the layers next to each other. Silicates are also network covalent solids. So here's a couple of examples. I think this is an example of glass, and this is something like quartz. So here we see that there's a very regular pattern formed by these different atoms. And again, we might think, well, that must be a molecular solid, right? It's silicon and oxygen. But it's not discrete molecules. Each of these oxygens is bonded to a silicon, to two silicons actually. And it's covalent bonds all the way throughout. So glass is amorphous, it doesn't have a crystalline structure. Things like quartz have a crystalline structure, an arrangement of their atoms. And these are going to also have high melting points. Yeah, glass is actually an extremely viscous liquid. They've done studies and looked at ancient windows, right? Windows that are hundreds and hundreds of years old. And they're slightly thicker at the bottom than they are at the top. But that process of movement is so slow that for all practical purposes, it is a solid. I know, it's crazy, right? It's like super, super viscous.
But what you just said, like, with the definition of the viscosity, like, that makes more sense. Right? That's the same thing.
Yeah.
Yeah.
Viscosity is the resistance of a liquid to flow.
Yeah.
So glass has very high resistance to flow. Yes?
Are plastics kind of the same way?
A lot of plastics are amorphous, meaning they don't have shape. And so it's possible, yeah.